Hello friends, welcome to this YouTube channel. Today we shall solve a couple of numerical problems on single phase transformers. By solving these problems, we shall learn how to determine voltage regulation of a single phase transformer while it operates at different power factors. We shall also learn how to determine power factors corresponding to zero voltage regulation and maximum voltage regulation. Let us have a look at the equations we need today to determine voltage regulation. Voltage regulation of a transformer is defined as the arithmetical difference in the secondary terminal voltage between no load and full rated load at a given power factor with the same primary voltage for both rated load and no load. Approximate voltage regulation at lagging power factor E2 minus V2 divided by V2 equals to I2 Req2 cos phi 2 plus I2 Xeq2 sin phi 2 divided by V2, or R per unit cos phi 2 plus X per unit sin phi 2. Condition for maximum voltage regulation cos phi 2 equals to R per unit by Z per unit or Req2 by Zdeq2. Expression for maximum voltage regulation E2 minus V2 divided by V2 equals to Z per unit. Approximate voltage regulation at leading power factor E2 minus V2 divided by V2 equals to I2 Req2 cos phi 2 minus I2 Xeq2 sin phi 2 divided by V2, or R per unit cos phi 2 minus X per unit sin phi 2. Condition for zero voltage regulation R per unit cos phi 2 equals to X per unit sin phi 2. Problem number 1. A single phase transformer has copper loss of 1.5% and reactance drop of 3.5% when tested at full load. We have to calculate its full load voltage regulation at unity power factor, 0.8 power factor lagging and 0.8 power factor leading. Let us first jot down the given data. Per unit resistance R per unit equals to 1.5%, that is equal to 0.015. Per unit reactance X per unit equals to 3.5%, that is equal to 0.035. Approximate voltage regulation at full load and unity power factor equals to R per unit, that is equal to 1.5%. When power factor cos phi 2 equals to 0.8, sin phi 2 equals to 0.6. Approximate voltage regulation at full load and 0.8 lagging power factor equals to R per unit cos phi 2 plus X per unit sin phi 2. Using values we get 0.015 into 0.8 plus 0.035 into 0.6, that is equal to 3.3%. Approximate voltage regulation at full load and 0.8 leading power factor equals to R per unit cos phi 2 minus X per unit sin phi 2. Using values we get 0.015 into 0.8 minus 0.035 into 0.6, that gives us minus 0.9%. Problem number 2. A 100 kVA 2000 volt by 200 volt 50 Hz single phase transformer has impedance drop of 10% and resistance drop of 5%. We have to determine the voltage regulation at full load 0.8 power factor lagging. We also have to determine the power factor at which the voltage regulation is 0. Let us first write down the given data. Per unit impedance Z per unit equals to 10%, that is equal to 0.1. Per unit resistance R per unit equals to 5%, that is equal to 0.05. Circuit power factor cos phi 2 equals to 0.8. Therefore, sin phi 2 equals to 0.6. Let us now determine the per unit reactance. X per unit equals to root over Z per unit square minus R per unit square. Putting values, we get root over 0.1 square minus 0.05 square, that gives us 0.0866. Approximate voltage regulation at full load and 0.8 lagging power factor will be R per unit cos phi 2 plus X per unit sin phi 2. Using values, we get 0.05 into 0.8 plus 0.0866 into 0.6, that gives us 9.2%. Voltage regulation is 0 at leading power factor condition, and condition for 0 voltage regulation is R per unit cos phi 2 equals to X per unit sin phi 2, or we can write tan phi 2 equals to R per unit divided by X per unit. Using values, we get 0.05 divided by 0.0866, that gives us 0.5774. Therefore, phi 2 equals to 30 degree. Power factor for 0 voltage regulation cos phi 2 equals to cos of 30 degree, that is equal to 0.866 leading. Problem number 3. A single phase transformer has percentage regulation of 4 and 4.4 for lagging power factors of 0.8 and 0.6 respectively. We have to calculate the lagging power factor at which the full load regulation will be maximum. Let us first jot down the given data. Voltage regulation 4% at 0.8 lagging power factor, when cos phi 2 equals to 0.8, sin phi 2 equals to 0.6. Voltage regulation 4.4% at 0.6 lagging power factor, when cos phi 2 equals to 0.6, sin phi 2 equals to 0.8. Expression for approximate voltage regulation at full load lagging power factor is R per unit cos phi 2 plus X per unit sin phi 2. Therefore, approximate voltage regulation at full load and 0.8 lagging power factor will be 0.8 R per unit plus 0.6 X per unit, which is equal to 0.04. Approximate voltage regulation at full load and 0.6 lagging power factor will be 0.6 R per unit plus 0.8 X per unit, which is equal to 0.044. Solving above two equations, we get per unit resistance R per unit equals to 0.02 and per unit reactance X per unit equals to 0.04. Now we shall calculate per unit impedance. Z per unit equals to root over R per unit square plus X per unit square. That is equal to root over 0.02 square plus 0.04 square. That gives us 0.044721. Now we shall calculate the power factor at which the full load voltage regulation is maximum. Cos phi 2 equals to R per unit divided by Z per unit. That is equal to 0.02 divided by 0.044721. That gives us 0.4472 lagging. Problem number 4. A 5 kVA 200 volt by 400 volt 50 Hz single phase transformer gave the following test results. During open circuit test, instruments were connected on low voltage side. Available data 200 volt, 0.7 ampere, 60 watt. During short circuit test, instruments were connected on high voltage side. Available data 22 volt, 16 ampere, 120 watt. If the transformer operates on full load at 0.9 power factor lagging, we have to determine the voltage regulation. Let us first jot down the given data. Transformer rating S equals to 5 kilovolt ampere, that is equal to 5000 volt ampere. Value of high voltage side voltage V1 equals to 400 volts. Let us now find the value of high voltage winding full load current. I1FL equals to S divided by V1, that is equal to 5000 divided by 400, that gives us 12.5 ampere. Now we shall determine equivalent circuit parameters from short circuit test data. Equivalent resistance referred to high voltage side Req1 equals to P copper divided by I1 square. From short circuit test data, we find that P copper equals to 120 watt and high voltage side current I1 equals to 16 ampere. Therefore, Req1 equals to 120 divided by 16 square. That gives us 0.46875 ohm. Now we shall find per unit resistance. R per unit equals to I1FL Req1 divided by V1. Using values, we get 12.5 into 0.46875 divided by 400. That gives us 0.01465. Now we shall calculate equivalent impedance referred to high voltage side. ZEQ1 equals to VSC divided by ISC. From short circuit test data, we find that VSC equals to 22 volt, whereas ISC equals to 16 ampere. Therefore, ZEQ1 equals to 22 divided by 16, that gives us 1.375 ohm. Now we shall determine per unit impedance. Z per unit equals to I1FL ZEQ1 divided by V1. Using values we get 12.5 into 1.375 divided by 400. That gives us 0.043. We have calculated per unit resistance. R per unit equals to 0.01465. Per unit impedance, Z per unit equals to 0.043. Now we shall calculate per unit reactance. X per unit equals to root over Z per unit square minus R per unit square. Using values we get root over 0.043 square minus 0.01465 square. That gives us 0.0404. Given power factor cos phi 2 equals to 0.9 lagging. Therefore, sin phi 2 equals to 0.436. Now we shall calculate approximate voltage regulation at full load and 0.9 lagging power factor, which is equal to R per unit cos phi 2 plus X per unit sin phi 2. Using values we get 0.01465 into 0.9 plus 0.0404 into 0.436. That gives us 3.08%. Problem number 5. A 30 kVA 6000 volt by 230 volt 50 Hz single phase transformer has primary and secondary winding resistances of 10.2 ohm and 0.016 ohm respectively. The reactance referred to the primary side is 34 ohm. We have to determine the primary voltage to circulate full load current with secondary short circuited. We also have to determine percentage regulation of the transformer for a load of 30 kVA at 0.8 lagging power factor. Let us first jot down the given data. Transformer rating S equals to 30 kVA, that is equal to 30,000 volt ampere. Primary winding voltage V1 equals to 6000 volts. Secondary winding voltage V2 equals to 230 volts. Let us now determine turns ratio. A equals to N1 by N2, which is approximately equal to V1 by V2. Putting values, we get 6000 divided by 230, that gives us 26.087. Primary winding resistance R1 equals to 10.2 ohm. Secondary winding resistance R2 equals to 0.016 ohm. Equivalent reactance referred to the primary side XEQ1 equals to 34 ohm. Let us now determine equivalent resistance referred to the primary side. REQ1 equals to R1 plus A square times R2, that is equal to 10.2 plus 26.087 square into 0.016, that gives us 21.0885 ohm. Equivalent impedance referred to the primary side ZEQ1 equals to REQ1 plus JXEQ1, that is equal to 21.0885 plus J34 ohm or 40.009 ohm at an angle 58.1908 degree. The value of primary winding full load current I1FL equals to S by V1, that is equal to 30,000 divided by 6,000, that gives us 5 ampere. Let us now determine primary voltage required to circulate full load current with secondary short circuited. VSC equals to I1FL ZEQ1, that is equal to 5 into 40.009, that gives us 200.045 volts. Given rating of the load SL equals to 30 kVA, that is equal to 30,000 volt ampere. Power factor cos phi 2 equals to 0.8, therefore sin phi 2 equals to 0.6. Primary winding voltage V1 equals to 6000 volts. We have calculated primary winding full load current I1FL equals to 5 ampere. Let us now determine load current referred to the primary side. IL dash equals to SL by V1, that is equal to 30,000 divided by 6,000, that gives us 5 ampere. Here we find that I1FL equals to IL dash because we have neglected no load current. Given reactance referred to the primary side XEQ1 equals to 34 ohm. We have determined resistance referred to the primary side REQ1 equals to 21.0885 ohm. Let us now calculate per unit resistance. R per unit equals to I1FL REQ1 divided by V1, that is equal to 5 into 21.0885 divided by 6,000, that gives us 0.0176. Per unit reactance X per unit equals to I1FL XEQ1 divided by V1, that is equal to 5 into 34 divided by 6,000, that gives us 0.0283. Approximate voltage regulation at full load and 0.8 lagging power factor will be R per unit cos phi 2 plus X per unit sin phi 2. Using values we get 0.0176 into 0.8 plus 0.0283 into 0.6, that gives us 3.11%. So today we have solved a couple of numerical problems on single phase transformers. By solving these problems, we have learned how to determine voltage regulation of single phase transformer at different power factors. We have also learned how to determine power factor corresponding to zero voltage regulation condition or maximum voltage regulation condition. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.